All right, so let's have a look at example 25. We know we're dealing with inverse functions. We need to find the inverse and sketch the graphs. So let's focus on the green function, which is the original graph. So y equals the square root of 2x plus 1. Again, let's aim to write it as the 2 out the front. That's obviously an x plus a half in that bracket there. Oops. And so we can see nice and clearly that in actual fact, the graph translates half a unit to the left, it's a square root function, and the dilation factor gets affected. So that gives us our green function over here on the left, all right? X equal to 0, y is equal to a square root of 1, which is 1. So we get our square root function over here. The domain of this function, we can see straight away from the graph, is from negative a half to infinity. The domain is from 0 to infinity. Our inverse function, swap the x and y values and then solve for y again. So that's what we've done over here in black. So we swap the x and the y, square both sides, take the 1 across, divide by 2. I get y equals a half x squared minus a half. So there's your x squared parabola, dilated, made a bit fatter, and shifted down half a unit. All right. So that's what we've got here. Turning point down half a unit. And we have half a parabola. Now, I guess there's a few things to comment on in here. Note that my x-intercept of negative a half 0 becomes my y-intercept of 0 negative a half. My y-intercept of 0 1 becomes my x-intercept of 1 0. So if you've got the features of one of your graphs, it gives you a lot of key features also then of your inverse function. Note that if I draw the line y equals x there in red, my graphs intersect along that line, all right? So I've got the domain and range of my original function, which gives me the domain and range of the inverse function, all right? So there's the key features there. Find the coordinates for the point of intersection. So in this case, I've got the square root of 2x plus 1. Now, I could let the two equations equal each other, is equal to a half x squared minus a half. But it's actually normally easier if we just solve one of the functions equal to x. So I've taken the square root of 2x plus 1 equal to x. We could have done a half x squared minus a half is equal to x. And we would get the same result. So if I square both sides here, I get 2x plus 1 equals x squared. Take the 2x and the 1 across. I thought I'd factorize it, because it doesn't factor nicely, so I'm going to complete the square. I could have used a quadratic formula. So if I complete the square, halve the middle term, square it, add it and subtract it sort of thing. So again, technically there's a few little things there, aren't there? I should have plus 1 minus 1. In other words, plus negative 1 squared minus negative 1 squared. And so I end up with 1 plus or minus root 2. All right, so my point of intersection up here is obviously my 1 plus root 2. If I was to extend both of these graphs, the 1 minus root 2 would be that point here. Okay, but since those graphs don't exist or don't, don't exist for that section or that domain, we don't have to worry about that point of intersection. Next part, show that f of f inverse of x is equal to x. So in other words, substitute the inverse function into the function. So the function itself in green, the square root of 2x plus 1. So instead of putting in x, I put in the inverse, a half x squared minus a half. Again, multiply the 2 through, we end up with x squared minus 1 plus 1. The 1's cancel, I get the square root of x squared, which is equal to x, which is what we were required to do. Example 26, find the largest value of d so that the inverse exists. So remember, the key thing here, for the inverse to exist, I need a 1-to-1 function. All right, so if I sketch the graph, and look, we need to be strong at sketching the graph. I've just factorized it there, x plus 2, which gives me x-intercepts at 0 and negative 2. I know the stationary point occurs halfway between them at negative 1. I also know the stationary point occurs at negative b on 2a, which would be negative 2 over 2, which is also negative 1. So there's a range of ways we can get the key features. For this graph to be 1 to 1, since my domain starts at negative infinity, I'm going to travel along here until it stops being 1 to 1, which is at the turning point, okay, which is at x equal to negative 1. So in that case, the domain to be 1 to 1 is from negative infinity to negative 1, and that makes t equal to negative 1. So now that we've got our function, we need to find the inverse. Now, y equals x squared plus 2x. I've got x in two different places. I need to consolidate so that x is in one point. So with my polynomials, it means I'm going to have to complete the square. There's no other way about it. So I've sort of taken the completing the square process just a fraction slower. So don't forget it's a half this middle term here. So a half of 2 is 1. 1 squared is positive 1. Then we minus 1 squared to keep equality. And so those first three terms become my perfect square, and I get a negative 1 left over. So that complements what we knew to be about our turning point at negative 1, negative 1. All right. So now I've got my function as y equals x plus 1 all squared minus 1. Now it's just a nice simple swap of my x value and my y, or x term and y term, I should say. And then transpose, bring the 1 over, take the square root of both sides, which means I get a plus or a minus. And then subtract the 1 across, I get y equals negative 1 plus or minus the square root of x plus 1. So there's always information that tells you whether you should do a plus or a minus, okay? Now, if we consider the range, I like to consider the range of G inverse, the range of G. So if we consider the range of G, we can see that the range is from negative 1. If I consider the domain of G, got myself confused. If I consider the domain of G, that's from negative 1 to negative infinity, or negative infinity to negative 1. All right. So that corresponds to the domain of the inverse. So if my domain has to generate really big negative numbers, it makes sense that I subtract the square root of x plus 1. All right. So that's how I know which of those plus or minus signs to have. All right. No, really important, we swap the y for G inverse of x, because that's the function we're dealing with. Never leave it as y equals. State the domain and range of G inverse. I didn't state the domain, did I? So the range of G inverse is from negative 1 to... No, it's not. That's the domain of G inverse. So let's just tidy that up. So the domain of G inverse is the range of, so let's just make sure, I might have had it right, let's just rub it anyway, just have a, make sure I've got it right. So the domain of G inverse is equal to the range of G, which is from negative 1 to infinity. The range of G inverse is equal to the domain of G, which is from minus infinity to negative 1. So hopefully that corresponds with what I had earlier. All right. Example 27, find the exact point of intersection for 1 on x plus 3 and its inverse. So again, you could work out the inverse function if you wanted to, but it's equivalent to solving the 1 on x equal to x. Yeah. So if I do that, so that's what I'm looking to solve. If I multiply both sides by x, I'll end up with a 1 plus 3x is equal to x squared. So it gives me a parabola now, a quadratic expression. So x squared minus 3x minus 1, up to you whether you complete the square, use a quadratic formula. However you want to solve that is best. I've decided to complete the square, keep me practice. Half the middle term is 3 on 2. 3 on 2 squared is 9 on 4. So I add 9 on 4 to be in my perfect square, which means then I have to subtract 9 on 4 to keep equality. And then I've got minus 4 on 4 there at the end, because that's my minus 1. So if we just go through, take the 13 on 4 across, again, take the square root of 13 on 4, which gives me root 13 on 2, plus or minus. So there's my x is equal to 3 on 2 plus root 13 on 2. Since x is an element of R plus, I don't have to worry about the negative root 13 on 2. So there's my point of intersection there. right? Oh, I missed that example, so let's do that. So sketch the inverse on the same axis. So note an asymptote at y equals -1, which means my inverse is going to have an asymptote at x equal to -1. So let's get a pen there. I'll just do it freehand. So there's x equal to -1. That intercept there is at the point 0, 2. So my new intercept is at the point 2, 0. My x-intercept at 1, -1, 0 now becomes an intercept at 0, -1. And so if I sketch that graph, there's my asymptote. There. And if I had the line y equals x in here, we can see that there's sort of a reflection about that line there. Okay. Let's consider the other graph here. All right, so same sort of thing. Let's just concentrate on this first square root function, if you like. We have an y-intercept at 1, 0, so that becomes an intercept at 0, 1. All right, and so again, to give us a bit of an idea, if I draw that line y equals x, we've got a rough idea maybe of where it goes. It's probably sort of out here somewhere. All right, but what often helps, let's just consider a point, say, I don't know, maybe that point there. That looks like the point about -9, 1, 2, 3, which means the other graph goes through the point about 3, -9, which is down here somewhere. So that makes it really clear for me now that the graph's going to go down like that. Whoop, that second one's. Just do one smooth curve. Something like that for that section. All right. What about, so this section here? Same sort of thing. What's that coordinate there about? Probably the point, I don't know, 2, -5, say, which means the corresponding point would go through -5, 1, 2, 3, 4, 5, 2, about there. We know that that point there is a point 0, -1, so the corresponding point is a point -1, 0. And so we're going to have a straight line sort of going through here like this. Yeah. So probably should erase the sections of the line that I'm not interested in. All right. So that gives us roughly what our inverse function should be. So let's get rid of that one. So there's my straight line off that way, and my square root function off the other way. All right, 29. Part of the function f of x equal to that is shown. Let h be from 0 to 2. State the range of h using exact values. So the range of h is determined by the domain, isn't it? So if we consider f of 0, 2 minus 3 to the 0, which is 2 minus 1, which is 1. F of 2, 2 minus 3 to the power of minus 2. 3 to the minus 2 is 1 over 3 squared, which is 1/9. So 2 minus 1/9 is 18 on 9 minus 1 on 9, which gives me the 17 on 9. So there's my range of values there, from 1 to 17 on 9. Find the inverse function. So again, swap the x and y values. So we've got x is equal to 2 minus 3 to the minus y. Bring the 3 across, if you like, the 3 to the minus y across, take the x over. So I get 3 equals 2 minus x. So the base, we're going to use our log base transformation. So log base 3 of 2 minus x will in fact be equal to -y. So that means my inverse function, f inverse of x, will be equal to the negative log base 3 of 2 minus x. state its domain. Well, its domain is just the range of the original, isn't it? And we worked out the range of the original just a couple of minutes ago. So, I hope that's all good. Example 30, consider the function. And the function, if the function h equal to f plus g, then the domain of h inverse is. So, all right, so first things first, what does the rule of h equal to f plus g look like? Well, there's f plus g, so it's that. What's the domain of that function? Well, the domain of that function has to be the intersection of the two domains themselves. Now, normally those respective domains would be R. The domain of f is R, but if we look at the domain of G, it's from 3 on 2 to 5. So that becomes the domain of my sum of the functions, okay? Because for whatever reason, we've decided that to define the function G is only existing from 3 on 2 to 5, all right? So that's the domain I'm interested in. So if I work out the rule of h of x by adding those two functions together, I get x squared minus 3x plus 3. I decided to do a quick graph sketch of that, and we get our turning point, and we sketch it over the domain that we've been told to sketch it over from 3 on 2 to 5. And at x equal to 3 on 2, the y value is 3/4. And at x equal to 5, the y value is 13. Okay, if we substitute those into the rule, which means the domain of h inverse is actually equal to the range of h, isn't it? And the range of h is 3/4 to 13. So notice I didn't worry about trying to find the inverse function, because I'm just rereading, and we didn't need to. All right, so consider the function f's defined between negative infinity to a, mapping onto r, where f of x equals x squared minus 2x minus 3. A, again, is the largest possible value, so the inverse exists. So again, we need the function to be 1-to-1. So you can see up here straight away, I've decided to complete the square on that function, okay, just to help find that turning point. And if I sketch the graph, I get a turning point at 1, -4. So I've only sketched the first half of the graph because my domain is from negative infinity to a. And so the a value I'm interested in is at 1, which is what I've got written here, because that's where my function is 1-to-1. So 1-to-1. Sketch the function and the inverse taking the domain and range for both. So if I sketch a parabola centered at 1, -1, 1, -4, it has an x-intercept at -1. We have that blue line there for the actual function. If I find the inverse function, again, I'm going to swap the x and the y. So notice the advantage of having the function already in a completed square form. If I've got it in turning point form, there's only one x, one y, there's only one thing I need to swap. So again, if I rearrange that, I get 1 plus or minus the square root of x plus 4. Again, do I want to use the plus or the minus? Determined by the domain of the original function. So the domain of the original function involves really big negative numbers. So I want to subtract. I want to have 1 minus the square root of x plus 4. From my original graph in blue, we can see that the domain of f is from minus infinity to +1, and the range is from -4 to +infinity. And so we're just going to swap those around for the domain and range of the inverse function. All right. Find point of intersection. I've decided to work with x squared minus 2x minus 3 equal to x form of the equation. So if I take the 3x across, again, I've got a messy sort of a function, x squared minus 3x minus 3. I want to solve that equal to 0. We can use a quadratic formula. We can complete the square. We can do either of those two things, really, because it's not going to factorise nicely. Half the middle term, which is 3 on 2. Square that, I get 9 on 4. So that's where those two terms come from. And then I'm going to solve for x. So x minus 3 on 2 all squared is equal to 21 on 4. Take the square root of both sides. I get root 21 over 2 because the square root of 4 is 2. So again, I get x is equal to 3 on 2 Again, we could have plus or minus root 21 on 2, but again, looking at where I am, the domain is from minus infinity to 1, so 3 plus root 21 is outside the domain I'm interested in. So my point of intersection, where x is equal to y, remember, so it's the same value, a half 3 minus root 21 for x and for y. I want that to be a red line. Just make sure my square root sign's over the top. All right, off you go.